All right, today we're going to take a look at section 10.2. We're talking about plane curves, so curves in the plane, and parametric equations. So to kind of develop the why are we doing this, that's the part that's at the beginning here, is that it's often convenient to describe location in terms of the parameter of time. Consider a batter hitting a ball. Its location depends on the length of time after it's been hit. Thus, we could talk about its two-dimensional location, where it is on the field, so not the third dimension of the height off the field, but where it is in a two-dimensional sense. In terms of x and y, with x and y, in terms of time. That is, there's an equation for x is dependent upon time, so x is x of t. And there's an equation for y is y of t. And these are called parametric equations. And all of what we're doing is going to turn three-dimensional toward, I can't remember which chapter it is, but it's not in this chapter. We are going to three-dimensionalize the ellipse, the hyperbola, the parabola from last time. We're going to do some three-dimensional pictures of those things. These plane curves are going to be three-dimensionalized as well in a later chapter, so we're building upon that. We are getting there eventually. Yes?
Well, you have to be good at drawing.
No.
Good.
It will be okay. You don't have to be good at drawing. I am not good at drawing, so it'll be all right.
I can barely do 2D.
All right, well, we're going to do some 2D drawings. In fact, we're going to do them today. In fact, we're going to do them in the next example.
Nice.
Sketch just for you. Okay.
Just for you.
Okay, just for you. Okay, so here's an example. This one says to sketch the curve defined by the parametric equations and write corresponding rectangular equations by eliminating the parameter. Okay, so there's a lot going on in there. And so we're going to do the sketch part first. Notice these equations are what kinds of equations? Trig. Okay. So as we think about what values we're going to do for plotting points, we want to choose values that are nice to work with inside of a trig equation. Now, not all of our equations are going to be trigs, so we're not going to choose the same values every time. It's context specific. So the first thing we're going to do is we're going to make a chart, a table of values. And our table of values is going to include three different columns. One column is the column for t, one column is the column for x, and one column is the column for y. Because we want to know where x and y are at any given time. Now, it makes sense that we would start at time 0. You don't have to start at time 0. You could start at something negative, but cyclic functions do this, right? They're just going to repeat. So we might as well start with 0. It's a reasonable spot to start. So if I put 0 into the equation for x, I would have 1 plus 2 cosine of 0. What's the cosine of 0? 1. So what do I get from this equation for x if I put 0 in for t? 3. And we're going to do the same thing for y. If we put 0 in for the t in the y equation, what will y give us? Negative 2. Okay, so everybody with me so far? And you could put these in your calculator if you wanted to, just in the regular the regular equations. You could put in 1 plus 2 cosine x into the y1. You could put in negative 2 plus 2 sine x into y2, and you could put in these values one at a time, and it would create the table for you. So don't go to too great of lengths to try and stress yourself out about finding these values. They're able to be found in lots of ways. We'll do this one just for practice out loud, like we're doing already, but keep that in mind. So thinking about your unit circle, because we're working with trig, what is a nice value that we might want to cross over next?
Pi over 2.
Pi over 2 would be my suggestion as well. So we'll go to pi over 2. So at pi over 2, what will x equal?
1, but cosine t is 0.
Right, the cosine t part would become 0, and then we'd have the 1 from the beginning, so we get 1. How about for y?
0.
That one actually is 0 because of the subtraction feature at the beginning of the negative 2. That's perhaps. What would be the next natural choice? Pi, you bet. Now, be careful. This is not perfectly symmetric, so you can't just go, oh, I'm going to change the 3 and the negative 2 from the first line. Things are not perfectly symmetric because we've got those constants in front added. So we do have to figure it. But if I put in pi, what will I get for my x value? Yep. And my y value? Negative 2. Good job. Okay. And our next natural choice, 3 pi over 2. So if I put in 3 pi over 2, what's my value for x? It is 1. And for y? Negative 4. And the final choice I'm going to make is going to be 2 pi. And at 2 pi, what's going to happen? We're going to get back to what we got at the very beginning, right? So we're going to get the 3 and the negative 2. Okay, so thinking about graphing this now, draw yourself an xy axis. All my values are between 0 and negative 4, I think, for y anyway, and between negative 1 and 3 for x. So I'm just going to hash mark out 4 in every direction. That should be sufficient. Okay, and we're going to plot these points, but I want to plot them in order, which makes sense. We're going to go down the table. But it's going to be helpful for us if we make sure that we're paying attention to the order in which we plot it for the next part of what's going on. So I'm going to change to using yellow. I'm going to first plot 3, negative 2. So 3, negative 2 would be right here on my graph. Then I'm going to plot 1, 0 would be here. Negative 1, 2. Whoops, here, negative 1, 2. My scale's not perfect, so forgive me in that. I have 1, negative 4. And then I'm back to the 3, negative 2. I need to connect these, but think about this reasonably. As we connect these, what shape is this creating?
A circle.
It's a circle. So you don't do connect the dots like on the Chili's menu for the children, right? These do not form a diamond or a square. Right? What?
No line shape?
No line shape. I do mention that on purpose because we're going to see something our calculator screws up doing and learn how to anticipate what should be happening and adjusting that in our calculator in a moment. So we're going to connect these. They are in a circular pattern. Looks something like that.
Oh, you have a tool.
I do have a tool. So it made it a beautiful circle, I know. Jill was with me earlier and saw just how beautiful my ellipse was, right, Jill? It was beautiful.
I don't know, my
Okay.
pretty good.
All right, so we need to do one more thing with a parametric equation that we don't do ever with rectangular. It just doesn't come into play. The whole point is that this is happening with respect to time, right? There's movement here, and we need to show the direction of the movement. So what we actually do is we draw arrows showing the direction in which those points got plotted, which is why we need to pay attention as we're plotting them so that we can put those in properly afterwards. Okay, we are going to come back to this one on your calculator in a minute, but we're going to do a different version of something first. So the next thing that the directions actually said is that it wants us to eliminate the parameter and find rectangular equation. Now, that's not directly obvious on this particular equation. So typically, I want to say typically, but a lot of times anyway, to change an equation into parametric form, we use substitution. So you'd take one of the equations, you'd solve it for t, you'd plug it into the other equation, and we'll see one of those toward the end of class. That doesn't work very well for this, right? These are trig equations. Isolating the t is going to end up giving us an arc sine and an arc cosine involved. Those are never very friendly for consolidating back together. That's not a good approach for trig, okay? So this is one of those exceptions to the rule. We'll see the one that's more the typical without the trig later. But what we can actually do on this one is we can actually use some properties of trig that you've seen before, but you probably may not notice immediately right now. So let me write down our equations that we have. We have x equals 1 plus 2 cosine of t, and we have y equals negative 2 plus 2 sine of t. And what I'd like to do is to solve each of these with the trig part by itself. It's fine if the coefficient stays with it, but I want to move the addition and subtraction to the other side. So the corresponding ones of these would say x minus 1 equals 2 cosine t, and y plus 2 equals 2 sine t.
Are we leaving the 2 there, or are we?
We're going to leave the 2 there. It'll get factored out later, and you'll see how nice it works, so it's good for it to be left. Now, there's a very nice property in trig called the Pythagorean identities. Do you guys know what I'm talking about? Remember those? Okay. If you don't remember what I'm talking about, we'll do an example here that shows you one of them, but there's 3 Pythagorean identities. The one we're going to use is that sine squared plus cosine squared equals 1. There's also ones for tangent and secant, and for cotangent and cosecant. And if you don't remember those two, because we don't use them quite as frequently, you can use, there's a trig, like a reminder sheet of some properties that's posted inside of Canvas. You're welcome to go and print that off. For the purposes of this one, it's the typical one that we're going to use. Now, let me show you how this works. I want to have a sine squared and a cosine squared here so that they'll eliminate and become a 1. Like, that's the goal. So here's the way that that happens. We take our x minus 1 and we square it, which correspondingly means on the other side of the equation we have a 2 cosine of t that gets squared because those are equal to each other. I just square both sides of the equation. I can do the same thing with the y. I have y plus 2 squared, and I have 2 sine t squared.
Oh, so we're adding our two equations
This is 2 steps in 1. Yeah, I squared each of my equations, so in some sort of sense right here, what I did is I squared this, I squared this, squared this, squared this, and then I added them together. Okay, everybody good? Because we want them to be added. We want to make use of that Pythagorean identity to eliminate the t. And I can eliminate the t because sine squared plus cosine squared equals 1. Now that's not exactly what I have just yet. The left-hand side is going to remain unchanged for a couple steps. In fact, maybe the rest of them, yeah, the rest of our steps, it's not going to do anything. But both of these have a 2 in them. So when I square it, I have 4 cosine squared t plus 4 sine squared t. They do both have a 4, which means the 4 can be factored out. That's why it doesn't matter if I move the 2 to the other side. And then, like we said, sine squared plus cosine squared is equal to 1. So this whole thing is equal to what? 4. Now, we didn't actually look at this equation in our conic section on Wednesday, I guess it was. We could have. You already mentioned it's a circle. It is a circle. You could also, if you think about dividing it by 4, consider it sort of an ellipse that's got symmetry, right? And it would look like the ellipse formula. But this is a circle. Where is it centered? At 1, negative 2. Is that where our circle is centered? It is. And what's its radius? 2. And what's the radius of our circle? 2. So you can verify once you're done that these give you those same like expectations. You expect that it looks like this. Okay? All right, I want to show you how to do a calculator with a different version, but we will do this one in a minute. I just want to do the regular one that's on the screen first, and we'll come back to this one. All right, so grab your calculator. And my batteries are low. We'll see if it holds out. You're going to click on mode. Yep, be in radians. That's important. Underneath the radian degree line, it's got one that says function. It says par, pole, SEQ, sequence. That's what it is. We're doing parametric. It's the second one, the one that says par, parametric, okay? Everybody good? Okay. Now, if you hit y equals, it actually takes you into a screen that you're familiar with, but it no longer looks quite so familiar. Do you see it has an x1 and a y1 and an x2 and a y2? Isn't it cool? Okay. All right, so we're going to put in the equations that it gave us, but don't go graphing it yet because we need to adjust the window before we do, okay? So go ahead and put in your t cubed is what will happen. When you press the button that says x, it's now going to say t. T cubed minus 2t and t squared minus 3. I'd like for you to hit window next. Now, your window could say a variety of things at this point. It doesn't, there's not a standard. It's going to be whatever is set before, whatever you've done before and in different environments. But we'd like for it to make sense in what we're doing. So again, starting at 0 is a reasonable place to start usually. So your t minimum being 0 is a good choice. Now, right now, my t max is actually at 2 pi. It actually says 6.2831 whatever. I've done something in relation to something that's trig recently, apparently, in it, or whenever I did it last. That's why mine says that. But these equations are not trig. So it doesn't really make sense that 2 pi would be the last place where it stops, right? Yeah. It just doesn't. So we're going to actually make it something that makes sense. And so let's do something that's like 4 or 6. I don't know. I don't have an example exactly what we're going to do. So just put something in that's a reasonable number. Maybe even put 10. I'm going to put 10. My T max is going to be 10. I think that's more than I need. T-step. T-step tells you how quickly it gives you new points. So, for example, when we just did our last example, our T-step was pi halves. we did pi halves between every iteration that we found the values for. Typically speaking, the bigger your t-step, the more rigid your graph looks, and the more, like the smaller your t-step, the more smooth your graph is going to look and more accurate. So just for the purpose of you seeing it, I'd like for you to use a large t-step right now. Let's just say t-step is 1, okay? I think that'll be sufficient enough to make it mess up.
Does this just make it like faster to calculate?
Yes. Yeah, so you don't want to just use the tiniest t-step possible or the thing's going to take forever to graph. So there is a delicate balance there, at least a little bit, in making your choice. The x-min, x-max, x-scalar, y-min, y-max, y-scalar is all stuff that we've seen before. So you can go with a negative 10 to 10 if you would like to use that. I don't know if that's exactly what we want, but that's what I'm going to put in for starters, and then we can adjust it later if we need to. Okay, so if you graph it, it graphed really fast, number 1, right? And it almost looks like a little bit of a boomerang action or something like that, right? Yeah. I kind of don't like that it looks really small on my screen, so I think I might change my x-min, x-max, y-min, y-max, at least to not include quite so much negative parts of the graph, because there's not a lot in the negative parts of my graph, right? All the 3 coordinates that are negative. So I'm going to change my window for my x-max to go from like -3 and my x-min -3 and my y-min -3, and see if that will help a little bit with what I'm seeing. And it does. But do you see how it looks really jagged now, especially now, right? It looks something like this on my screen, right? Really jagged. Now, that doesn't make sense, because if you look at these equations, these are polynomial equations. They're nice and smooth. They should be nice and smooth. They shouldn't be jagged. Now, go in and let's change something else. Let's change our t-step. Let's make our t-step 0.1 instead. Now, graph, and you'll see it's going to take it longer to graph, but isn't that much lovelier, that's a good word, isn't that a much lovelier graph than we had before? Oh, okay. I thought there was a problem. Okay, so it looks something like this. We want to be accurate in how we're drawing it. It looks like it's starting at -3. And it looks like it crosses here at about 2. So my graph looks like this, and, oops. Oh, it actually looks like it crosses here too. And again, the direction is doing this. Any idea how you might describe the image you're looking at? Can you tell what it's supposed to be or trying to draw?
Looks like it's part of an ellipse.
Maybe part of an ellipse.
Or
Maybe part of a parabola. Okay, so let's change one more thing so that we can see maybe a better picture. It started where it started because our t-value is 0, right? What if we started with a t-value that was smaller than that? So let's make our our window have a t minimum, or t minimum of, say, -10 this time. I probably need to get some more of my y value negative on my graph. So I'm going to make my y minimum go down a little further than it was before, so maybe like -6, I don't know. And we'll see.
I'm sorry. She did something. What?
That was a little,
Oh my goodness.
What the?
a little goofy.
Did it do what you thought?
Nope.
Wait, hang on, what?
He's a little loopy-loop.
Did you graph it, Maggie?
I did.
Okay, do your t minimum. Make your t minimum -10 instead,
To 10t.
and just graph. What'd it do?
A little whoop.
You got a loop on there. You can't do that in rectangular equations very much, can you? That's not easy to do. So, in terms of this graph, we have the same image, but it's flipped over the y-axis. That completes the other half of this graph. So it looks something actually like this. It's still moving in this direction, by the way, but this gives me the complete image, or more of the complete image of what I thought I was expecting to have.
I never thought you could have.
Isn't that interesting?
Like that.
Okay, so let's take a moment and let's go back and look at the one we did before. We'll do some other stuff with it later. You'll see. Yeah.
That could be a
I know
position.
what real world application.
I know.
Take the derivative of.
Okay.
the velocity.
All right, hey guys, do this with me. Do this with me. Go back to the original graph that we had over here. That one. Let's put in the x and the y that are in the trig one that we did. So x is 1 plus 2 cosine t. And y is -2 plus 2 sine t. Now, our scalar, all my window stuff, is going to be quite different. I did my t-scale, went from 0 to 2 pi, right? So I'm going to do 0 to 2 pi again for that one. You can put t-step at 0.1 if you want to, but just for the moment, I want you to see something funny that happens. Put it as pi halves. Make your t-step pi over 2.
It shall be a rectangle.
And then, again, let's go from like -4 to 4. That's what we did when we kind of drew it. So we'll do -4 to 4. And when you're ready, go ahead and graph it. What'd you get?
Little diamond.
You got a diamond. Did everybody get a diamond?
No.
Wait, mine's like a rhombus.
What did you set your?
Well, people call it a diamond. It's not a very good accurate
Well, I
thing.
mean, like,
What did you set yours?
Technically a rectangle.
he's like a,
In and out
wait,
of
what's yours
there.
like?
The T-min and the T-max,
Mine was
I put
diamond.
at 0 and 2 pi, just like we did on our table.
You have to set
T-min
your
0,
T-step
T-max
and
2 pi,
Yeah.
and I made my
Like-
T-step pi
It depends
halves,
on-
because that's how I did my iterations on the
Like it.
screen. Every pi halves is when I
Well,
found the
say that's your
value.
window. You change your window, it'll change how it looks.
Yeah, so over here, this is a good mention, like, is it a rectangle, is it a rhombus, is it a square, is it a, what do we have here? Do you know what the shape is?
Technically, a rectangle is all the way below.
Rectangle or square?
Well, a square is a rectangle, so.
True,
You
but
can
you
call
could
it
be more
rectangle.
specific. Is it more specifically a square on this one?
This would be a square because it's a circle.
Yeah, this one's a square. Now, it doesn't look like a square,
Circle, I like it.
in part because the window is not, like, this window itself is a rectangle, so the scale is looking funny at you, and so it doesn't really look quite
Zoom.
right. If you hit zoom square,
If you hit
number
zoom
5,
square, it'll make it-
the square window, you see the square.
Yeah.
Right, what?
Zoom.
The square window actually makes it fit in the square the way it should, because this is a
Oh, yeah, that made my
zoom
worse.
square.
Mine-
Do you guys have your scale off?
Check your equations on that one. I don't think your equations are entered
Equations?
right. Yeah,
1
No,
plus
they're
2
good.
sine, -2 plus 2 sine.
it's -2 plus 2.
Yeah.
Oh, your step is off. Oh, never mind. That's
Let me
good.
take a look. Your graph's not looking like mine.
Oh, you put your max is different, that's why. Two,
What's the number?
pi.
Oh, check your,
The
zero,
because
your
your
team
team
in.
That's still the same.
No,
But-
it's right.
Zero's still -10.
But you got the.
No, that's
Monster
right,
also.
she's right.
Oh,
Yeah,
I
make
think
it
that's
put
what
mine
mine
at
is
two.
doing.
Zero, two,
Because
five.
when I plugged it in earlier.
0 to 2 pi.
Okay.
Plugged it in earlier.
All right, everybody good? Now, is it really a square?
No.
I mean, we drew a circle. How did we draw a circle when they drew a square? Well, because we did our T-step to use only those 4 points. And what the calculator does is the calculator draws on the children's menu the same way, right? It connects the dots. So just for a moment here, change your T-scale to make it, we'll just go back to 0.1. That should probably be okay, and press graph.
What a fun little guy.
Yeah, I'm gonna go smaller. 'cause
And
that's-
what do you get now?
The circle.
It's the circle we expected, right?
Oh, that's why.
Yeah.
It's a perfect circle too, I can't draw that.
Yeah, it's lovely. Calculator does a good job when we get to T-step that's small enough.
What have I done?
Yeah.
Okay.
500.
What have I done?
Okay, you guys ready?
Yeah.
All right, so on this one, I thought that I had an example, but I guess I didn't. When we eliminated this parameter, we did it with this trig substitution thing. If we were to try to do this one, this isn't a great example, but let's just pretend for a moment that we tried. We could take the second equation, the y equals, and we could solve it for t pretty easily, right? Maybe not x equals, that's more complicated, but we could solve the y equals equation for t. And we could actually take that value and we could plug it in for the t's into the x equals equation and eliminate all the t's. And we would have an equation in terms of x and y. It won't be a function, but it will be an equation in terms of x and y.
Would it make something close to a standard circle?
Not on this one, because we're going to get this funny loop thing going on, and there'd be no way for your calculator to graph that in a rectangular, like the typical screen you're used to graphing it in. If you were working on something like Desmos or something, there's probably features in there that you could use.
Okay.
Yeah, I haven't played with it, but I'm pretty sure.
I've never seen one.
I know, it's a fun graph. Okay.
Yeah, you just needed 0.0.
All right, let's talk about finding parametric equations, though. So taking parametric equations and finding their corresponding rectangular equations is a very direct process. I mentioned the substitution. We did an example with trig. Doing it the other direction has a lot more flexibility that can create, Alex's equations to look different than Adeline's equations. Like, that's possible. But I want to show you some steps that you can think about on doing this. And so it just means that whenever I grade things, I have to be more careful to make sure that what you have works. So, directions say, find a parametric equation, or find parametric equations describing the given curve. So this curve's very simple. We're starting on purpose with it simple. It's just a line segment. Starts at one point, goes to another point. You can picture this. Starting at a point 1, not a curve yet, no. Starting at the point 0, 1, ending at the point 3, 4. Okay, everybody good so far? Okay, so I'm going to be doing a fair bit of writing, which might help you, Jill, from what we're talking about today, of wanting to be able to go back and read some writing about what's happening. So we're actually going to think about what's happening to our individual points. So what is x doing? Well, x goes from 0 to 3. Oops. So far, so good. I feel like that I gave you guys a tool that you're super excited about, and now I need to take it away.
Except like 0.0001.
It's still graphing, isn't it?
It's going so
This
slow.
is why you can't do this.
Here,
Okay.
yeah, now make your T max
And I have
like
like
500.
Okay.
And I have like the new one. So.
All right, guys. Let's keep moving, all right? All right, from 0 to 3. It does say it's a line segment, right? So when I've got a line segment, I'm going to have linear pieces for both x and for y. Now, what's the standard form for an equation for a line? One that's easy for us to use that you remember very well. Y equals mx plus b, right? Now, we're going to write it with x equals, because our equation is x. And I'm going to use at plus b. If you want to use mt plus b, that's fine. But you do need to use t on the right-hand side and x on the left. That's not negotiable at this point. Okay, we have to decide what we want our t max and t min to be, just like we did in the calculator. This is where you have flexibility. You can pick something obscure. Please don't pick something obscure on purpose. I'm looking at y'all for it because I just sense that this is going to happen. Okay, you can pick kind of whatever you want. The easiest pick is really to go from 0 to 1. Okay, so we're going to let t go from 0 to 1. So we want to create an equation y or x equals at plus b, that when I plug in 0 for t, I get back 0 for x. And when I plug in 1 for t, I get back 3 for x. Okay, we do this all the time in our regular rectangular systems. In essence, what I'm doing is if I'm writing these as ordered pairs, or you know what, I'll do it as a table. I like that better. If I had t and I had x. If I let t be 0, I want x to be 0. And if I want t to be 1, I want x to be 3. This is what's supposed to happen. Okay? So these are like ordered pairs. Like you could do this and you could calculate the slope, right? So if I look at this, my y-intercept is 0, clearly, because I've got the point 0, 0 listed here. So the b in that equation is 0. What's the slope? If you were to calculate slope, m or a, yeah, we could calculate slope, right? The change in y, in this case it's the change in x over the change in t. It would be 3. Right? If I went up in t1, I went up in x3. So this equation is x equals 3t. Okay, we did it for x. Now we're going to do the same thing for y. Okay, so this is sort of step 1, kind of like a bulleted point, step 1. Step 2 says the same thing. So y goes from 1 to 4. And again, it's linear, so y is equal to at plus b. Now, these a and these b are different a's and b's, so if you want to subscript them or something to identify that separately, go for it. But again, in terms of a table of values, we have to let t do the same thing. Whatever you chose for t to do with x, you have to have the same t doing it for y. So you don't get flexibility in this one. Whatever you did before, you have to do it again.
So, pick when t goes from 0 to 1, y goes from 1 to 4?
Mm-hmm.
Okay.
exactly.
So if you picked a different, like let t go from, I don't know, 2 to 5 or
Yes.
something?
You'll still get, you'll still have to do 2 to 5 for both of them. Your equations will look different, but they'll still work.
Okay, so they would look the same.
Yeah, you'll end up with the same graph, you'll end up with, all the things will still end up the same, and we can even graph this in our calculator when we're done to make sure we really see that line that starts at this point and ends in that point. We'll be able to see that. So you can check it.
It's weird that any 2 points would work.
And there are points that are honestly sometimes more convenient to use. I mean, 0 and 1 are nice here, but if I was doing trig stuff, it wouldn't be nice. We wouldn't want to do it that way, right?
0 to pi or something?
Yeah, you could do something with 0 to pi or 0 to 2 pi or something like that. So again, t and y now. So when t is 0, y is 1. And when t is 1, y is 4. So if you take a look again, we actually have the y-intercept. The y-intercept this time is 1. What's my slope?
3.
Yeah, slope's 3 again. Now, the slope doesn't always become 3. That's just the way it was on this particular example. And those two together combine to form my parametric equations. So let's try it real quick and make sure it worked in the calculator, okay? So in the first equation, you're going to put the x is 3t. The second one is that it's 3t plus 1. We need to make sure our window really goes from 0 to 1 only, because we set those parameters for t. Starts at 0, ends at 1. Your t-step being 0.1 is probably just fine. It's really not a big deal on this one, but it should be okay. And then if you want to mess with your x-min and x-max, it just needs to have these it's supposed to go from 0.01 to 0.34. So I'm just going to go like negative 5 to 5 would be probably fine. And we'll graph it. So you get a very unexciting little piece of a line segment?
Yep.
Yep. Does it visually look like it starts at 0, 1? And did you watch it move toward the right-hand side and go towards, what was it, 3, 4? Did it do those things? Yeah. So that's one way I can check your work too. If you decide to do something a little bit less normal, then I can check and see if it still works. Yeah.
So if it goes backwards, like
You end up with a negative value somewhere.
Okay.
Yeah. So if you think about what happens with a negative slope, it'll go the other direction. So you can actually move the other direction. Like on ours, we went from a positive, like we went t is 0 to 1, right? But if the x had gone from 3 to 0, it just would have been a slope of negative 3.
Oh.
So you would have ended up getting a negative slope for your parametric equation associated with x. See ya. Okay. Now, the line segment's not super exciting. The next example is a little bit more involved just because the equation turns into a curve. So let's take a look at that one. Oh, also one other thing, when we're writing this, we need to identify, we wrote it down in words, but our t-value is starting at 0 and ending at 1. That's part of what we're doing here. That's our parameter, right? So if you checked later, you'd have to use that in order to check to know that you did it right. We talked about it, but we didn't write it down in the inequality form. Maggie, you look confused.
I'm just kind of confused as to how this is an answer. Like,
It wants parametric equations,
yes.
which we have. We have an x and we have a y.
Yes.
And it satisfies the conditions because it starts at 0, 1, the point in the xy plane, right?
Yes.
And it ends at 3, 4. So that's what we're looking for. We're looking for parametric equations that produce a certain result.
Okay.
And like we keep talking about, there's lots of them. It's not a one and done kind of thing on a right answer. There's lots of right answers. So that's why even in my directions, I was I was not very direct. It doesn't say find the parametric equations, right? It says find parametric equations. Because there's lots of parametric equations that will do this. It just depends on what you chose for your t values because it's going to fix what happens on x and y.
I totally had in my head that this was related to number 2.
Oh,
No,
it is not related to number 2. Gotcha. Okay, let's do one that looks a little different. So in some ways, this one's easier than the other one because it's got a little bit more information, but it's not a line. We don't get a line graph on this one. So it wants a portion of a parabola. The parabola is y equals 2 minus x squared. So we actually have an equation that we're trying to get to this time. but only the portion that goes from 2, -2 to 0, 2. Okay, that's the portion of the equation we want. Now, you probably know what this equation looks like. What is the equation? I mean, I know it's a parabola, but tell me something about this parabola, this specific parabola.
Starts 2 down.
It starts 2 up. So the origin we go up to, and then what did you say, Caleb?
Points down.
It opens downward. Okay, so generally speaking, our graph has this sort of a shape to it. Right? But it says that it's going to be only a portion of this. It's going to start at 2, -2. So 2, -2 means down here like this. And it's going to end at 0, 2, which means this. So we're only going to get this part of the graph. That's the only part of the graph we're supposed to get by the parametric equations that we create. Okay, do you have a sense of what you're looking for?
Is that supposed to be another -2, comma -2, or because wouldn't it be the right side? that you'd
I did
want?
it wrong. I did it at -2, -2. Sorry, let's go the other direction. In fact, this one answers the question, Adeline, you had about going the opposite direction. I thought I had one. 2, -2 would be here, over 0, 2. So it goes like this. So thank you for that. I didn't have this graph drawn as my problem in my notes. I just thought I could do it on the spur of the moment, evidently. So, okay, so it looks something like that up there. That's awfully tiny. Sorry, I didn't realize I was drawing so small. That's better. Okay, is that all right? That's what we're looking for. So here's what we're going to do. We again need to let t do something. Now again, if you wanted to let t go from 0 to 1 each time, that's totally fine. However, there's a lot of 2's involved here, so I'm going to choose that t is going to go from 0 to 2. It's just a choice. You get to make the choice. I'm choosing to let t go from 0 to 2. So let's let t go from 0 to 2. I said that right.
Quick question.
Yeah.
So you've always written this down as a lowercase t.
Mhm.
On the calculator, it's always a capital. Is there a reason why?
That's a good question, and I don't know the answer to that. Every time I see it in text, I see it as a lowercase. It's only in the calculator that I see it as a capital T, so I'm not sure.
Okay.
But there is probably a reason. Yeah. What's x doing?
It's going
Increasing.
X goes from what to what?
2 to 0.
Yeah, it goes the other direction, right? It starts at 2, and it goes to 0. So it's exactly the opposite. Now, we do have a curve here, but the curve is going to be taken care of when we get to the y equals equation. We can still do this much like we did the last one with identifying what happens with t and with x. So when t is 0, x is 2. When t is 2, x is 0, as such.
I'm confused about where these values for x are coming from.
They're coming from the points that we were given.
Okay.
So we're given the points here. So x is 2, the x coordinate is 2, and the second one, the x coordinate is 0.
Okay.
So they come from the ordered pair points that were given.
Okay, so we just pick random values of t.
Correct, to
say-
some degree, yeah. And I picked 0 and 2 just because I saw that the points in my equation, I got a lot of 2's in my equation, so I feel like it's going to work nicely. And if I'm wrong, I can always change it to something different. So, so what is my y-intercept? My y-intercept, my x-intercept. Like in my equation, x equals a t plus b. What is the b value from this table?
2.
2. Why 2, Alex? Everybody else is looking at me like that. They're not sure what I'm asking, but you got the 2. So where'd you get the 2 from?
Because it's where it started.
Yeah. So remember when we're talking about like a y-intercept in our traditional algebra kind of sense or whatever, when x is 0, the y value that corresponds to it is my y-intercept. In this case, it's the same thing. When t is 0, the value that corresponds to it, for this case x, would be the 2. Okay? What's my slope here?
One.
Negative.
Why negative, Caleb?
It's the other side.
Yeah. And if you weren't sure, could you just find the slope? Like, could you calculate m or a? Sure, you could. You can do your change in this case x over the change in t. You can also think about what's happening here about the fact that as this one goes up, right, it increases, this one is going down. So it's a negative change. Okay, so this equation right here, x equals negative t plus 2, is the parametric equation I'm going to use for x. But I already have an equation for y. What's my equation for y?
Do you just substitute it?
I do. There's the substitution finally we're getting to, like I mentioned, right? This is the equation that has to follow for x and y. This is how x and y correspond in the rectangular coordinate system. So I can simply replace the x with what x equals, which is 2 minus t now, or negative t plus 2 if you prefer. And we solve this. Oh, and it's squared. There we go. So this is 2. It'd be minus 4 plus 4t and minus t squared. If we distribute all that together. Moving things in order, I'll put the negative t squared plus 4t and minus 2. Do a little bit of algebra cleanup. But parametric equations have to be accompanied by the t interval we chose. That's what determined it. If I had chosen a different t interval, my parametric equations would not look like this. They could be equally as correct, but still look different. What is my interval for t?
0 to 2.
Yes. And I think we should check this. I think it's a good place for us to end class today. So go ahead and put the equations that we're getting into x1 and y1. And you want your t min to be 0, your t max to be 2. And just based on what we've already sort of thought through in our graph, as long as we can stay in that negative 5 to 5 window, or if you want to make it a little bit tighter, maybe in like negative 3 to 3 or something like that, we should be good to be able to see things. My t-step being 0.1 seems the reasonable place to leave it. If it starts graphing too slow, we can make it bigger. If it's graphing too rigid, we can make it smaller. But it's a reasonable place to start. Do you get the graph you were expecting to get? Yeah. So it is really important as you work through these to have some sort of intuition about what you expect. What is the expected result? Because we're working in a very different graphing system than we're familiar with. And we have to keep that in mind. I expect my graph should look like this, because if I make a mistake and it doesn't, I want to know it. And if I don't have an expectation going into the graph, then I don't have a way of knowing very well if what I'm looking at is unreasonable. Does that make sense? Okay.